So what we want to do in this video is remind ourselves something that we already know. We want to look at systems that have two equations and two unknowns, or in other words, two variables, and we want to graphically recall how solutions play out for those types of systems. So here I have three systems of two equations and two unknowns. So for example, this system right here has two unknowns or variables, x and y. I have two equations, and so we know when we have two variables, x and y, that we're playing in the Cartesian plane, and we know that if as long as the exponents on the x's and y's are ones, that we have linear equations. And that's the type of equation we're looking at right here. This is systems of linear equations into unknowns. And what we remember from previous classes is that the things are going to play out in one of three ways. We either get two lines when we graph them that intersect in a single point, and this corresponds to our getting a unique solution. In other words, the point of intersection is the solution to the system. So if we were to solve this by elimination or substitution, any of those techniques that we've learned, we would get a single point of intersection. But there's another way in the plane that two lines can play with each other. They can lay right on top of each other. So for this system here, what I have is two lines that when we graph them lay over top of each other. So they have infinitely many points in common, and the lines themselves turn out to be the solution. So this is a case where there are infinitely many solutions, because there are infinitely many points of intersection between the lines when we graph them. But the third way that two lines can play out in the Cartesian plane is they can be parallel and non-intersecting, and this would correspond to our getting no solution. So really these are the only three ways that solution sets can occur if we're working with systems of linear equations into unknowns in the Cartesian plane. We either get independent, dependent, or inconsistent results corresponding to a unique solution, infinitely many solutions, or no solution at all. So for example, if I asked you the question and said, is it possible to get, that's a horrible two, to get exactly three solutions? If we have a system of linear equations, the answer would be no. It's impossible to get exactly three solutions when we have two linear equations in the Cartesian plane. We either get one solution, infinitely many solutions, or no solution at all. We can't get exactly 3 or exactly 15 solutions. That's not one of the geometric possibilities. And just as an aside to introduce the idea, when we're working in linear algebra, we typically aren't going to use x's, y's, z's for our variable names. So it would be more common, for example, for this first equation to be written only with x's, but subscripted x's. So we would usually write 2x sub 1 minus 3x sub 2 to discriminate between the two variables. And similarly, this would be, that's 6y, so this would actually be 5x sub 1, and then I would go plus 6x sub 2 equals 4. It would be more common to write the system using subscripted x's as our variable names.